Hi, my name is Johan van der Grenendel, and I'll be presenting Delivering Telemetry at Scale with Intel and Splunk. Our co-presenters are Jason Conger and Maurice Oriel. In today's presentation, we'll go over the background, collecting telemetry at scale, OpenBMC as a telemetry delivery vehicle, Intel's autonomous crash dump technology, the Intel OpenBMC plugin features, and a demo. The data center continues to grow in complexity with more processing elements, memory devices, smart NICs, all within a given density. Workload demands on these resources is increasing as data continues to explode and the application of AI increases. Data center managers need the ability to monitor all elements in the data center in real time and at scale. They need increasing visibility into real-time error information, as well as collecting the state of the system in the event of a failure to enable rapid root cause. Part of the solution is to be able to do advanced data collection at all levels of the data center, the ability to apply analytics to predict failures and aid in efficient and effective root cause, and having a BMC plugin that is able to stream telemetry collected out of band and aggregated from multiple platform components. The general telemetry at scale architecture consists of three distinct layers: the instrumentation, collection, and analysis layers. At instrumentation, this is the instrumentation of platform components, firmware, BIOS, and drivers. At the collection layer, the ability to collect this information and stream it out of band to an at-scale database. And then a set of tools that allows for searching, analyzing, and visualizing machine-generated data in real time. Together, Intel and Splunk have implemented a reference design of the generalized architecture. Intel CPUs provide a rich amount of telemetry out of band, as well as the ability, in the event of a failure, to perform Intel autonomous crash dump. The OpenBMC plugin is able to push redfish event metrics, BMC cell logs, as well as any ACD information collected to Splunk in real time. In addition, Splunk has the capability of accessing customer data like inventory and RMA information, as well as absorbing any other data in the data center that might be relevant to the analysis. Once in Splunk, Splunk provides a rich set of capabilities including dashboarding, eventing, the ability to do correlations, and apply analytics to all the data within the database. Intel Autonomous Crash Dump technology is the eye in the system, or the canary in the coal mine. The CPU has information as to what might have caused the failure. An example is uncorrected memory errors is a leading indicator of a memory DIMM problem. Intel Crash Log technology captures a comprehensive set of data from the processor, including core state, which includes general purpose counters, machine check registers, MTRR, super queues, uncore information including transaction status of what was in flight at the time of the crash, including memory and I/O transactions, and detailed uncore state including machine check registers, various status and configuration registers. As part of the reference architecture, Intel has developed a small utility that assists in through isolation. The utility can be applied to any crash dump that is collected, and it displays a summary of what might be the leading causes for the failure. Splunk is a universal machine data platform. It allows for the correlation analysis of data from multiple data sources. In addition, it has a rich set of capabilities to report and analyze the same data in different ways, including IT operations, security, business analytics. In addition, it supports enterprise scalability. We will now give you a brief demo. Once we've logged into Splunk and selected the Intel dashboard, we have four options: crash dumps, metrics, server inventory, and RMA. Let us first drill down into crash dumps. On this view, we are able to see crash dumps over time. So on the first view, you can see the number of crash dumps as a series on a per day basis. We also break down the crash dumps by bio version in a textual format as well as a graphical format. The BMC version over time has a graphical format. crash dumps by Ucode version, as well as Ucode version over time. Next, we're going to go look at the crash dumps at a data center level. In this view, we are able to see which racks or which systems within a rack had a crash dump and the number over time. In addition, we can see a list of the latest crash dumps in which we can drill down and take specific event actions. In this case, we are going to use the Intel crash dump analysis tool to determine what might have gone wrong. Taking the data we've displayed is a summary, the machine check architecture, as well as the table of requests. In this particular crash dump, we see that we had a watchdog timeout, which resulted in a Tor timeout, which might have either been a memory transaction or an IO transaction that caused the system to stop executing. Next, we go back to our previous view, and in this view we can see a detailed list of what crash dumps have taken place, what rack, their BIOS version, BMC versions, the type of CPU, and the OS image that was running. Now we're going to go and look at some data center metrics. As we described earlier, Splunk is able to natively handle redfish events. We select some BMC temperature. We'll go back the last 30 days as we recorded this quite a while, and there you can see the real-time data of the temperature being sent to Splunk on a periodic basis. Next, we'll go look at some data center metrics. Here we can see the temperature by rack. So in this example, you can see we had some hotspots on system GC160 and ER232, as well as some excursions elsewhere in the data center. And down below, we can see what the average speed of the host was. This is a representation of some issues that we've often seen in the data center, where there was a cooling problem in a particular location of the rack, and using a combination of this data, it would help us determine why certain systems may actually be performing badly or having issues. Next, we'll go look at server inventory. Here we have a breakdown of BIOS versions, CPUs, Ucode versions, BMC versions, and OS images. This can be very important in doing crash analysis, as it may be related to a particular BIOS or CPU or Ucode version that might be more susceptible to a particular problem. And finally, we go look at the RMAs. RMAs are systems that were repaired. We go look at how RMAs correlated to a BIOS version, to the BMC version, as well as we can look at the top fault reasons of what actually took place to go redress the issues. So for example, in most cases, memory was replaced the majority of the time, and in other cases we see FPGAs or CPUs or motherboards being replaced to go and address the issue. Our call to action: use the OpenBMC plugin when available, starting in May 2020, extend the data center telemetry with additional components, build example analytic models, collect and store the data center telemetry. If you'd like to see a live demo, contact myself and we will arrange it. Thank you.
I don't see any questions being posted, so thank you very much for listening. We are available in the Intel booth if you would like to ask any additional questions or rewatch the demo. Thank you very much for attending.
Thank you very much for attending.